the turbulent flow, and first we will do some introduction. Of turbulent flow. Now, let us look into some of the characteristics of turbulence. First one, it means irregular motions. Turbulence means it is basically an irregular motion, and there are random fluctuations. Now, there are random fluctuations of velocity field with respect to time. Now, what are the origins of these random fluctuations? It may be from the surface roughness, this fluctuation is basically it may come from surface roughness. What is the surface? It is basically the confining conduit through which the flow is occurring. It is basically the wall surface roughness. And secondly, fluctuation may be due to the difference in velocity of the adjacent fluid layers. Okay. Now, this fluctuation can grow with time or it can decay with time. Under what condition it will decay with time? The viscous forces may dampen the fluctuation. If that means close to the wall, it is highly expected that in the effect of the eddy forces or eddy terms in the turbulent flow will be less prominent and the viscous forces will be dominant. Okay. So fluctuations may be dampened by viscous forces, or it may be magnified. How it gets magnified? It may take energy from the free stream velocity and the fluctuation may grow with time. Okay. Now, how to understand that whether the fluctuation will be dampened and what will be the quantitative criteria by which you can say it is a turbulent flow? The irregular fluctuation will increase with time or it will decrease with time. It is dependent on a dimensionless number. All of us know about that. That is the Reynolds number. There exists a critical Reynolds number. Okay. If your Reynolds number, your operating Reynolds number is less than critical Reynolds number, typically the critical Reynolds number is 2000 to 2200 for a flow through a tube. Okay. And if it is around in the order of 10 to the power 5 for flow over a flat plate, the critical Reynolds number. Now, if your operating Reynolds number is less than critical Reynolds number, then the fluctuation will be dampened by the viscous forces. The viscous forces will be dominant. Okay. So, turbulence of the flow will be dampened. If your Reynolds number is operating Reynolds number is greater than critical Reynolds number, then your fluctuation will grow with time and you are totally in the turbulent region. In fact, there is a region where both turbulent terms and the viscous forces are dominant, equally important, that is basically transition. So, you might be getting a thin transition region where it will be transiting to the total turbulence, complete turbulence. Okay. So, let us write down the origin of turbulence. One is what we said, the surface roughness. So, friction forces from the solid wall. This is called wall turbulence. It may be originated by the difference in velocity of the adjacent fluid layers, that is called free turbulence. I am not writing it full, it is basically velocity difference, as we said discussed earlier, velocity difference between the adjacent fluid layers. So, it is a free turbulence. Okay. So, basically these two are roughly the origin of the turbulence, and let us discuss what turbulence does. Turbulence means there is a lateral mixing of the fluid particles. So, it will give you a better mixing. Okay. And it gives you additional diffusive effect, right. Diffusion in the, suppose there is a flow in the x direction, in the axial direction, it gives a better mixing in the normal direction. So, that is the physically what turbulence does. Now, let us look into some of the schematic of velocity field. If you plot u versus t, okay, for a completely fully developed laminar flow, you will be getting almost a constant velocity, and this velocity u is basically the area averaged velocity. Okay. Now, for turbulent flow, so this is for the laminar. There may be small fluctuations, but those small fluctuations are basically measurement errors. Okay. Now, for the turbulent flow, you might get random fluctuation about a mean point. All kind of fluctuation. Okay. And this is basically the mean velocity around which the velocity will be fluctuating. So, in the turbulent flow, you will be having you will be having two parts, the mean velocity, and there will be time dependent fluctuation will be imposed on the mean velocity, and you will be getting a fluctuation of the velocity something like this, and this fluctuation is absolutely random. It is very difficult to quantify this fluctuation. Okay. So, later on what we will be doing, we will be basically exactly like the laminar flow, we got the velocity profile by solving Navier-Stokes equation. The Navier-Stokes equation or the equation of motion will be slightly modified for the turbulent flow, and obviously your aim will be what will be the velocity profile under a turbulent flow. Okay. In order to get the velocity profile under the turbulent flow, you have to quantify these random fluctuations. Now, since these fluctuations are entirely random in nature, then how will you quantify this fluctuation? That will be one point. Now, there are two approaches. First approach is by using the chaos theory. This is total chaotic condition, right, this fluctuation. By using chaos theory, you can quantify this fluctuation. You can propose several models, empirical models, semi-empirical models, means you do some experiments and relate the terms with the operating conditions, etc., and you propose some empirical models for extra terms, those will be appearing in the Navier-Stokes equation. What we will be seeing later on, I will be probably in this class only, that in the form of Navier-Stokes equation under the turbulent flow, there will be extra term appearing in your equations known as the Reynolds stress terms. Now, the origin of these Reynolds stress terms are from the random fluctuation of the velocity field. So, the standard way, it is a very old method, you propose some of the empirical relations to relate this Reynolds stress term with the velocity or the velocity gradient, and substitute in your equation and then solve the equation. Once the relationship is known with the velocity or velocity gradient, then there will be no problem for you for solving or getting the velocity profile. But you remember all those relations, there are several like Prandtl's analogy, Bosnick's approximation, von Karman's hypothesis, etc., but all these relations are empirical in nature. Okay. So, under certain conditions they have conducted some of the experiments, measured something and Reynolds stress probably, and related those terms with the velocity or gradient of the velocity and expressed those equations. Now, it may not necessary that whatever the values you are calculating for the mean velocity or whatever after getting the velocity profile, that will match exactly with your experimental value, but that will be close to that. Okay. Now, let us look into the velocity profile of the two regimes. Suppose there is a flow through a conduit, it may be a circular conduit, that means a tube. For the laminar flow, you will be getting a parabolic profile for a fully developed velocity field under the laminar flow condition. For the turbulent flow, you will be getting a profile something like that. There will be a sharp increase or very close to the wall, because at the wall you will be having the no slip, zero velocity, then velocity will be increasing continuously. Okay. And you will be getting a sharp increase in velocity very close to the wall, and then that velocity will be almost constant throughout the whole cross section of the tube. Why this is sharp? Because you will be having viscous forces dominant close to the wall. Viscous force will be more dominant close to the wall, and it will be less dominant in the middle of the channel or middle of the tube, right? Because middle of the tube, the fluid particle may not experience the existence of the wall. Okay. But on the contrary to the laminar flow, your viscous forces will be dominant entirely throughout the cross section of the channel. This is known as the plug flow. Here the velocity is assumed to be constant throughout the channel. So, this is the velocity profile for the fully developed laminar flow, this is the velocity profile for the fully developed turbulent flow, and this is an entirely plug flow velocity profile. That means velocity profile is constant. Now, here u is varying as a 1 minus y square by r square, something like that, y square by h square, and here it will be varying with a certain form of variation. It will be function of y, but it will be independent of y. The typical one may be flow of a toothpaste, that is basically a plug flow. Liquid metals, that is basically plug flow.
So, in turbulent flow the Reynolds number is less than critical Reynolds number?
No, greater than critical Reynolds number, because less than, if it becomes it is less than critical Reynolds number, the viscous forces will be dominant and dampening will be there, and turbulent fluctuation will be dampened. So, the best way to understand whether the flow is laminar or turbulent, you compute the Reynolds number and check whether it is greater than critical Reynolds number or less than critical Reynolds number. Critical Reynolds number is around 2200 for flow through a tube, it is around 5 into 10 to the 5 for flow over a flat plate. So, based on that you can do your judgment. Now, let us quantify the mean motion and the fluctuation. Let us say for a parallel flow, parallel flow means flow through a in a rectangular channel or flow through a tube. Your u as a function of y and t may be expressed as there will be two components. One is the mean velocity. In the previous we have seen it is a mean velocity around which the fluctuation will occur, and u prime is the time varying fluctuation. Okay. So, this is basically time averaged part, and this is the time varying part. Now, how to quantify the time dependent fluctuation? We will say the definition is, over the long term the time dependent fluctuation will not contribute anything to the bulk flow. Okay. In the short time it might be having some effect, but in the long term it won't be having any effect on the mean bulk flow. That means the integral over minus t to plus t some time period u prime dt will be equal to 0. That will be one of the assumptions. But the turbulence will grow due to interaction of the velocity fields. Okay. So, due to interaction, the interaction terms of the velocity field will exist. That means the interaction term, the product of u prime and v prime, the integral over the time period will exist, and that will give rise to the that will represent the turbulence in your flow field. Okay. So, let us write down the time averaged quantities. Time averaged terms. U prime bar must vanish due to its definition. This bar is basically averaged over time. The time average of u prime v prime will exist. Okay. So, basically we quantify our turbulent motion as a summation of mean velocity plus time dependent fluctuation. So, we write down different velocity fields in terms of this u prime bar and time dependent fluctuation. One will be u bar plus u prime. U bar is basically the mean velocity and u prime will be time dependent fluctuation. V will be v bar plus v prime. W, the z component velocity will be w bar plus w prime. Pressure will be p bar plus p prime. All the dependent quantities will be divided into two parts. One is the mean time averaged part, another will be time dependent fluctuation, and it will be considered as it will be this will be all these dependent terms will be a linear combination of this time independent part and time dependent part. And by definition, the time averaged quantities of all these time varying part will be equal to 0. That is by definition. Okay. Now, let us look into the physical effects. Let us try to define the how it affects physically to a system. These fluctuations u prime, v prime, w prime will affect the mean motion in certain way, okay, and it results an apparent increase of viscosity as if. It results apparent increase in the viscosity or the momentum diffusion. Now, in order to obtain the velocity field under the turbulent flow conditions, there are certain algebraic rules that have to be followed. These are known as the Reynolds rules for time averaging. Now, if you have f as f bar plus f prime and g, there are two quantities, let us say f and g is g bar plus g prime, then the time average of f plus g will be simply time average of f and time average of g. Okay. Time average of c, a constant, a scalar multiplier multiplied by f, should be c time averaged of f. Time average of del f del x should be differentiation of the time averaged quantity of f with respect to x. Okay. And this is important, this will give you the interaction term time average of f and g. You just substitute f is equal to f bar plus f prime and g as g bar and do the calculation. You will see that you will be getting, sorry, this will be f prime g bar plus g prime, and do the algebra, you will be getting bar of f bar g bar plus f prime g bar plus g prime f bar plus g prime f prime. Okay. And now, if you open up this time averaging quantities, this will boil down to f bar g bar plus time averaging of f prime g prime, because when you open up this time averaging, the time averaging of f prime individually will be equal to 0, because g bar is always a constant with respect to time. It is already time averaged, so it is independent of time. So, by definition f prime bar and g prime bar will be equal to 0. So, you will be getting this. So, that will be this will be important for the cross terms. Now, let us look into the general equations. General governing equations for to quantify the velocity profiles under the turbulent flow condition. Let us look into the, for the first instance, for incompressible flow. That means rho is independent of time, rho is constant, basically the your density is constant, and the equations, governing equations for any velocity field, as we have discussed previously in the previous semester, that it will be considering 4 equations as far as the velocity field is considered. One is equation of continuity, second is x momentum equation, y momentum equation and z momentum equation. These 4 will constitute the equation of these 4 equations will specify the velocity field. You will be having only one equation, that is the energy conservation equation under the in the differential form for the temperature field, and you will be having n minus 1 number of differential equations for n component system as for the concentration profiles. And what is the last one? The last one will come from overall material balance. Under any whenever you will be doing a practical problem, then you will see it is very difficult to match the material balance. If you write down n number of concentration equation, species balance equation then you will see that you cannot match the material balance. Then no one will buy your idea in your plant, because you are putting some material, you are getting some material after reaction, maybe it may be a reactive system. So, the total material that is coming in should be total material that is going out in terms of kg per hour, and in most of the cases you will be considering a very costly material. So, if there is some mismatch in your material balance, it precipitates a very high consumption of your money, cash flow. It will alter the cash flow. Okay, so either it will be very expensive, or you cannot in your calculation you cannot consider that loss, or it may be if you are calculating more, then that is also very spurious, because in your practical life you will see that you will not be getting that much. So, it is very it is very urgent to, it is an emergency situation to write down to match the material balance under any engineering calculation. So, for the species balance, if there are n number of species existing in your system, you write down n minus 1 differential equation, okay, and solve these equations and find out the concentration of or material that is going out for all these species. And the last one, that you can identify any one of them, okay, the last one should be obtained from the overall material balance. In that way, you have to check that at every point of calculation, or suppose it is a long tube, let us say it is a tubular reactor. Okay, so you have to check that whether you will be matching your material balance at every point of cross section. Okay, that is important. So, we write down the equation of continuity. It will be simply del u del x plus del v del y plus del w del z for your the equation of continuity. Now, you substitute u by u bar plus u prime, v by v bar plus v prime, and w by w bar plus w prime, and write down here, okay, and substitute these terms there. So, you will be getting del u bar u prime del x plus del y of v bar plus v prime plus del z of w bar plus w prime will be equal to 0. Right. Now, take the time averaging of the previous equation. Now, this time, whenever we are talking the time averaging, now this time averaging is basically long term time averaging, but in the short term there will be fluctuation of the velocity level. It is like a flock of birds flying. Okay. So, generally it will be having a motion in a particular direction with a mean velocity, but within the flock there will be the minor variation of the velocity as well as the magnitude of the velocity and direction of the velocity of each identical bird. But overall the flock will be having a mean velocity in a particular direction. The mean velocity is the one we are discussing, and the intermediate fluctuations will be basically the time varying fluctuation, and these two will be superimposed and it will be giving the turbulent motion. Okay, now if you take the time averaging of the previous equation and use the using the Reynolds rule, of averaging, you will be getting del u bar del x plus del v bar del y plus del w bar del z equal to 0, because your u prime bar, v prime bar, w prime bar is equal to 0 by definition. Is that clear how you got this? you take the time averaging of the previous equation. In this equation, you take the time averaging, so it will be like this, right. Now you go to the first rule of Reynolds averaging rule. Okay. So it will be a summation of u bar and u prime bar. Bar of u bar will be obviously u bar, because that will be constant, right, and u prime bar will be and bar of whole thing will be u prime bar, the second term. So u prime bar is equal to 0 by definition, v prime bar will be equal to 0 by definition, and w prime bar will be equal to 0 by definition. So you will be getting del u bar del x plus del v bar del y plus del w bar del z equal to 0 as the equation of continuity for the turbulent motion. So basically equation of continuity will be remaining its form, it will be keeping its form intact compared to the laminar flow, only the dependent variables like the velocities will be time averaged velocities or time smoothed terms. Now let us look into the x component equation of motion. Now let us write down the equation of motion: rho del u del t, u del u del x, v del u del y, w del u del z is equal to minus del p del x plus mu del square u del x square del square u del y square plus del square u del z square. Okay. And rho gx, let us say gx is equal to 0 for a horizontal flow. So that component will not be there. So it is basically the inertial term which will be associated with density, mass, inertia. So it is called inertial term. This is the pressure fluctuation, pressure variation term. These are the viscous terms because they will be associated with the viscosity of the fluid. Pressure term, viscous terms, and we are considering the body force term because it is we are considering a horizontal flow. So gx, the component of g in the x direction will be equal to 0. Now again you put the definition of u, v, w, p. U is equal to u bar plus u prime, v equal to v bar plus v prime, w equal to w bar plus w prime, p is equal to p bar plus p prime, and substitute and use the Reynolds averaging rules. I am just writing the final equation because it is a long algebra, and that is there is no point in doing that algebra. You can look into any of the standard textbook like Bart Stewart Lightfoot or your what is that one Fox and McDonald, any standard textbook you will be getting these intermediate steps. So the final outcome will become rho del u prime del u bar del t plus u bar del u bar del x sorry, this will be v, this will be u, you will be getting the viscous terms, okay, del square u bar del x square mu times del square u bar del x square plus del square u bar del y square plus del square u bar del z square. Then you will be getting some extra terms. So, basically you will be getting these extra terms after simplification. So, what is the difference between the x component equation of motion between the laminar and turbulent flow? In the laminar flow, you will be getting up to this part. In the turbulent flow, everything will be identical if you replace the dependent variable by time averaged quantities, and these extra terms will be appearing. There is no way to exactly theoretically quantify these terms. These are called Reynolds stress terms. Okay. Now, there are different empirical relations of these terms, these Reynolds stress terms with velocity or velocity fields are available in the literature. They are obtained by conducting several experiments and developing a correlations between measurements and the independent variables, and this using those empirical relations you can substitute those here in terms of velocity field, mean velocity field or gradient of the mean velocity, and then you can solve this equation in order to obtain the velocity profile with respect to time as well as with respect to position. Okay. Yes. No, actually, these time fluctuations are basically small time fluctuations. No, this time is basically long term variation. If it may be transient turbulent flow, this equation is basically transient turbulent flow. In that case, your mean velocity will be function of time, and this time averaging we are considering it is basically averaging over very small time scales. Like a flock of bird is moving in a particular direction, okay, at a different point of time the mean velocity may be different, but the actual the internal velocities, the variations of those with time, they will not affect the mean velocity. That is our assumption. So, this term will correspond to the transient turbulent flow, and that this time is basically long term time variation. And whenever we are doing the time averaging, these are the short, we are always discussing the short time fluctuations. Now, okay, so you will be having, we introduce some of the notations. Okay, and this bar is basically the time averaged. So, tau bar xxt is rho u prime square bar of that. Okay, so these are called the turbulent momentum flux. Okay, you see look into the similarity of the laminar momentum flux, the shear stress, that is mu times velocity gradient. Now, the turbulent shear stresses are defined like this. They are obviously connected to the velocity field, and different turbulent stress terms will be given by the correlations with respect to the mean either mean velocity or the gradient of the mean velocity. So, you can write the equation of motion in the compact form. So, this is the material derivative. It has two components, one is local derivative and another is the convective terms. This is the that is a temporal one, and the the time average pressure, the gradient of shear stress corresponding to the laminar term. This if you simplify this term, it will be giving rise to mu del square u del x square plus del square u bar del y square plus del square u bar del z square. And these are the extra terms, the Reynolds stress terms are represented by this gradient of momentum flux, momentum stresses under the turbulent flow conditions. And now, by semi-empirical correlations, this turbulent stress term will be given as a relation, as an empirical relation with respect to the u bar and either the velocity or the gradient of the velocity. Those will be inserted in the equation, and it will be slightly, there will be some extra terms, and you can still then you can solve that equation in order to get the u bar, that is the velocity profile. Okay. So, there will be empirical or semi-empirical relations of the Reynolds stress terms are available, which will be incorporated in the equation of motion in order to get the velocity field. Now, let us look into some of the semi-empirical expression. The first one we will discuss is known as Bosnick's eddy viscosity. It simply says, exactly like the Newton's law of viscosity, it says tau xy bar, that is for the turbulent part, will be is equal to mu du bar dy, and this mu is not for the laminar one, it will be mu turbulent. It is exactly like the Newton's law of viscosity. Now, in Newton's law of viscosity, the viscosity is basically the fluid property. That will be constant, that will be a function of temperature. For an isothermal condition, that will be constant for a particular fluid. That will be a function of temperature as well as the composition of the fluid. So, that will be an inherent property of the mixture. Now, this mu t will be a function of location, because this represents the turbulence, and turbulence is absolutely random. So, obviously, that will be a function of location. And now, how to define that function of location? That is very difficult. Okay. So, what people do? People take some average velocity of mu turbulent, which will be roughly 10 times higher, or maybe even higher, 10 times, 50 times higher than the viscosity of the laminar fluid. Like for water viscosity, what is the water viscosity? At the room temperature, it is around 1 centipoise. Mu turbulent may be 50 centipoise, 70 centipoise, 100 centipoise. Okay. So, some average viscosity will be considered in this equation, and then it will be substituted in your governing equation, then you can solve the velocity profile, right. This is exactly similar to the Newton's law of viscosity. Mu t is known as the turbulent coefficient of viscosity, or it is sometimes called eddy viscosity. Okay. So, once you know the eddy viscosity, then you can insert this expression in your governing equation and solve the equation in order to get the velocity profile. Then second relation that we will be discussing is well known as Prandtl's mixing length analogy. It is similar to the motion. It is similar to the kinetic gas theory. We assume that the fluid particles or eddies, turbulent eddies, move like random gas particle in your system. Okay. And based on the in the kinetic gas theory, you have the one parameter is the what is the one parameter is free what is that called mean free path. So based on the mean free path, you will be having the Prandtl's mixing length and the expression for the turbulent shear stress or the Reynolds stress term minus rho L square du bar dy mod of that du bar dy. Okay, and L is roughly equal to 0.4 y ky. L is proportional to y and this proportionally constant is roughly 0.4, and this value is obtained from various experimental observation. That is why it is called empirical. Okay. So, the shear stress here is a function of location as well as the velocity gradient. So, this can be inserted in your equation and you can solve the equation and can get the velocity profile under the turbulent flow conditions. So, the effective eddy viscosity in this equation will be roughly, it will be rho L square du bar dy, right. That will be the effective eddy viscosity. The shear stress is equal to mu times velocity gradient. So, this will be roughly mu effective and this will be the velocity gradient. So, mu effective in this case will be rho L square du bar y dy. Okay. Then one more equation that we will be discussing, that will be pretty important. Okay. So, that will be von Karman's hypothesis. Okay. It gives another expression of turbulent shear stress with the velocity gradient and the location. Then you will be having a relationship close to the wall, because close to the wall the viscous terms will be dominant and the turbulent eddies will be less dominant. So, that is called Dissler's correlation, that will be valid very close to the wall. Okay. So, there are several relationships available in the literature. Now, if someone wants to say that what will be the accuracy of this equation, suppose you will be using one equation, you will be landing up with a solution. If you use the another equation, you will be landing up with a different solution, but all these will be very close. If you ever compute of any of these four analogies, I will be discussing the another two empirical relations in the next class. If you take any one of these four, or if you compute all the four and then compare, you will see there will be little difference. And the fourth one, the Dissler's empirical relation, that is generally valid for very close to the wall. Okay. And there are several efforts later on has been tried out that how to combine one equation. So, actually if you look into the velocity fields under the turbulent flow condition in a tube very close to the wall, the viscous forces will be dominant. Okay. Just beyond that, towards the center of the channel, there will be a region where viscous force and turbulent eddies both are equally important. And roughly around middle of the channel, you will be having completely turbulent flow. The eddies term will be dominant and the fluid particles residing in those portions will not experience the presence of the wall. There will be no effect of viscous term. So, there will be distinctly 3 regions that you can get in a fully developed turbulent regions, and you will be having various relationships for shear stress for these 3 regions, and you can simplify your velocity profile as well, because the Disler's relation will give you the velocity field close to the wall. Okay. Now, that will probably constitute 1% of the full channel, right? That will constitute 1% of the full channel. So, whatever that is, that effect will be negligibly small. Okay. So, anyway, we will be discussing these these expressions later on in the next class, and how to obtain, and we will be probably solving one example how to obtain the velocity field using one of these, a couple of these relations. Okay.